case you missed it in the opening, this is the second video in a series of videos. If you haven't seen the first video, you might want to go back and watch it. The first video was about prototyping and designing the circuit that we're integrating with this Getaway pinball machine. This second video is about the integration. So let's open up the machine to get an idea of what we're integrating with. Take the glass out. You have to take the balls out when you lift the playfield, otherwise they'll roll all over the place. I gotta find the right solenoid. There it is. So the playfield just lifts up. Getaway has this cool hinging mechanism that makes this operation a lot easier. Some of the older games don't have this locking hinge, and the even older games don't have a hinge at all, and the playfield is just loose. I remember the first time I saw the inside of a pinball machine, I was astonished by how complex the underside of the playfield is, and just how many components there are, and how much wiring there is. With the playfield up, we can see the inside of the cabinet and the underside of the playfield. The cabinet only houses a few components. There's the coin mechanisms in the coin box, the line filter in this metal box. This is the tilt mechanism. There's a large power transformer, one of the cabinet speakers. There's a prop bar that you can use to prop up the playfield. But most of the stuff is mounted to the underside of the playfield. First thing you see is there's tons of wiring. Every one of these components has cables that has to make its way back to the back box where the circuit boards are. So I pointed out a few of the components. Sometimes you'll find printed circuit boards under the playfield. These two control the supercharger mechanism. There are always solenoids. That's these guys. These little solenoids control the pop bumpers. And there are similar solenoids up here for the kickers that are above the flippers. All of the beefy solenoids in this game are flippers. So this is the upper flipper mechanism. The solenoid pulls in this armature, and that makes the flipper move. So you have an upper flipper here, and then the two flippers at the bottom of the playfield. These large circuit boards are lamps. So these sockets just twist out, and there's a incandescent light bulb in each one of them. Some of the lamps are mounted in sockets like this. You notice the diode mounted on this lamp socket. That's unusual. All of the lamps in pinball machines have diodes. If you're used to working with solenoids, then you're used to seeing diodes across solenoids, like these here. But so you have to have diodes across inductors, but it's unusual to see them across lamps. The reason that those diodes are across lamps is so that the lamps can be matrixed. So there's tons of wiring here. because each solenoid, each lamp has to have a conductor that feeds it power and then a way to ground that back to the back box. So you've got 2 conductors for each lamp, and there's 64 lamps in a pinball machine. That would be tons of wiring if each one of them had a conductor out to the playfield and back. Not to mention you've got flash lamps and solenoids that have the same kind of wiring. Pinball machines are manufactured, at least assembled, by hand. So there's tons of work that goes into soldering all these connections and mounting all these sockets and running cables back and forth to the back box. So to reduce the amount of wiring, they've matrixed the lamps, and that's really important later when we're talking about how to integrate the circuit into the lamps in the playfield. So the lamps that we're wanting to integrate are these. These are the tachometer lamps. So some of them are on sockets like this, and some of them are on circuit boards. They make their way back to the back box on a few different connectors. There's these 3, and then of course these wires. So I don't want to integrate my circuit here because there are several different places I have to tap in. I really want to do it in the back box. So let's take a look at what's in the back box. Keep my back box key and the coin door so I don't lose it. This just lifts out. So let's take a look at these circuit boards. Let's take the dot matrix display out so we can see more of the circuit boards. This just lifts out. So Getaway is one of the early Williams pinball controller systems, or WPC for short. The board set looks a lot different than some of my other games. I'm not as familiar with this one. But this board here is the CPU. That's the actual CPU on the board. But this whole board is colloquially referred to as the CPU board. This is the Fliptronics board. So previously the flippers were a lot more rudimentary, and the cabinet switch that controls the flipper actually had the full flipper voltage on that switch, and you just by hitting that switch you'd actuate the flipper. Starting with this generation of game, Williams went with a computer-controlled flipper. So, hence the bus to the flipper board from the CPU board. So this is the Fliptronics board. This is the audio or sound board. This board controls the dot matrix display. And this large board is the power driver board. So you'll see tons of transistors here, and those large capacitors that power the solenoids and the lamps on the playfield. The connectors of interest to us are these this series of connectors here. These are all the lamp connectors. So I said before there are 64 computer-controlled lamps on the playfield, and you'll see that there aren't 64 wires here. There's 8 wires on these connectors, and 8 wires on these connectors. That's because of the matrixing scheme that Williams employed. So if it weren't for matrixing, you'd see a lot more wires coming in here, and there'd be a lot more manual labor required to assemble the game, and it would cost a lot more and take a lot longer to make. So we'll come back to the power driver board later when we're integrating with it. Let's get it buttoned up. So let's take a look at the operations manual for Getaway to learn more about the lamp matrix. The operations manual has tons of information. There's general information about the playfield and gameplay, game setup, there's a surprising amount of configuration and tests you can run that are built into the machine. You can, of course, change the pricing of the machine. But you can also change gameplay, replay values, sound. There's a full breakdown of all the machine parts, including diagrams of all the boards and a list of components on the boards. There's a whole separate manual for schematics that give you the schematic for everything from the power supply to the driver board and even the CPU. But what we're looking for here is information about the lamp matrix. So I mentioned there's a half mile of wiring in the machine. There would be a lot more wiring if it weren't for matrixing. For instance, there are about 64 lamps in a modern Williams pinball machine. Each one of those lamps would require a positive line and a ground line to light it. So that's a lot of wiring that has to go from the back box under the playfield to the lamp and then all the way back. To avoid doing that, the engineers at Williams designed this matrixing scheme where a single wire can come down and connect to 8 different lamps, and then another wire can go back and touch 8 different lamps again. So you have, to power 64 lamps, you've got 8 wires coming down, 8 wires going back. Each one of those wires powering or grounding 8 lamps. So you can, with one loop from the back box back to the back box, you can control 15 different lamps. So it works by putting a lamp at the intersection of the 2 wires with a diode, and then the machine pulses power on column 1, 2, 3, 4, 5, 6, 7, 8, and then on each one of those columns grounds lines 1, 2, 3, 4, 5, 6, 7, 8. So because of our persistence of vision, we see that a light is solidly on, when really it's not. It's pulsing very rapidly because the machine's multiplexing so many lamps very quickly. when I'm trying to integrate this tach with the playfield tachometer lights, it's not as simple as just looking at whether a lamp is on or off, because the lamps are on and off a lot. Very often they flash very quickly. And I can't just tap into one line and see if there's power on it, because if I want to look at this lamp, I'd be tapping into this line. Well, anytime any of these 8 lamps are on, I would see power at that line. So I have to look at whether I have power and then whether I have a ground. The easy way to do that would be to just break this line and put my circuit in series with the lamp and the diode. But unfortunately, lamps run on PCBs in most cases, so I can't break the trace. So my theory is I can make a parallel lamp matrix where I run another line off this and another line off this, and kind of make my own little circuit off to the side to see if that lamp is on or off. Pinball machines run at various voltages. Typically a DMD display runs at about 100 volts. The solenoids run at normally either 70 or 50 volts. The flash lamps run at 20. The lamps on the lamp matrix run at 16. The switch matrix runs, I think, 5 volts. And you've also got AC current for the general illumination that's about 6.3 volts, I think. You may have noticed when we were looking under the playfield that all of the wires terminate at bare solder joints. So there's a lot of uninsulated connections. There's also a lot of bare reed switches and unprotected lamp sockets. So it's really easy to cross wires and get radically different voltages on a circuit that you aren't expecting. Typically that'll blow fuses, it'll blow transistors, often it blows ICs on the driver board, and it's not hard to do that. So when I'm integrating with the pinball machine, I want to make sure to keep my circuit isolated as much as possible from the machine, just in case that happens. I don't want to blow up my circuit or my microcontroller. Also, I'm kind of new at electronics, so if I screw up my circuit, I definitely don't want to screw up my expensive pinball machine. So I've been looking at optical isolation as a way of making sure that no matter where I screw up on the pinball side or on the this tach circuit side, that I don't break the other one. Optocouplers or opto-isolators are really simple. The one I've been looking at is the 4N25. It's a 6-pin IC. On one side there's an IR LED between pins 1 and 2. On the other side is a transistor, a phototransistor that opens this connection between the collector and the emitter based on the LED lighting. So it's responsive to the infrared coming out of the LED. So when power is applied here, proportionate power is passed through here. If the LED is off, then nothing is passed here. So there's an air gap right here. So it's a way of isolating two different circuits, and they're really simple to use. So I'm thinking that's a good way to join the two circuits without having a potential to pass power between them. I could start by, in fact, powering all of my circuitry through a different power supply, and completely isolating the two circuits. If I get confident that I've got everything right, then I could power my circuit from the pinball machine power supply, because, as I said before, there are a lot of voltages available. So there's really no reason to run a separate power supply for my circuitry, aside from the fact that I just want to be careful. So I've got a 16 volt bench supply driving this breadboard, and then of course my old breadboard running off 12 volts. So here's the optical isolator. You can think of this bottom section is running on 16 volts, and this top gets 5 volts from the other breadboard. So the lamp matrix runs at 16 volts. So this is my way of kind of prototyping getting a lamp matrix signal and driving the micro at 5 volts from that signal. So we can hook up some test leads. I'll put one on the ground side on the 5 volts, and one on the 5 volt positive. So you can see we're reading 5 volts, and if I hit the button that closes the 16 volt side, it drops down to 0. You can see the bench supply. The current goes up a bit when it's driving that internal IR LED in the opto. But what that tells me, when the voltage goes from 5 to 0, is that closing the 16 volt side is also closing the 5 volt side. So the transistor inside the opto, the emitter is grounding, causing the collector side to go to nearly 0 volts. So that's exactly what I want to see. So the activity on the 16 volt side is driving activity on the 5 volt side. The basic stamp model that I'm using has two different kinds of memory, RAM and EEPROM. RAM's a lot faster, but it's very limited. If we take a look at the memory map interface offered by the basic stamp IDE, you see RAM here and EEPROM here. You can see that the program that I've written so far is using almost all of the RAM. These blocks are bits, so I've got 32 bytes left. Not very much. So every time that I declare a new variable, I'm going to start using up the remaining 32 bytes. So I've only got about 4 variables I can declare before I completely run out. Meanwhile, over here, you can see I'm hardly using any of the EEPROM. I've got 7FF, 2K of EEPROM, and I'm using only a quarter of it. So most of the space that I'm using in RAM are the potentiometer offsets. So I've got 15 bytes I've declared to store those offsets, and I'm storing those in an array, which means I'm storing them in RAM. It would be much better if I didn't take up that RAM and if I stored those in EEPROM. So that's what I did. You can see on the next rep of the code, I'm using the data keyword to store the same offsets in EEPROM. It's a small change to how you access that memory, but it makes a huge difference in storage. You can see now I'm only using a fraction of my available RAM, and I'm taking up 15 bytes in EEPROM. So it's a really good trade-off, because I rarely read these values. So a little bit of delay to get them out of memory is not a big deal. Meanwhile, there's a lot more I want to do with this code, and if I hadn't moved these values out, I wouldn't have any space with which to do it. So I've hooked up a simple circuit to the power driver board on the pinball machine. You can see I've got test leads hooked up to the column and row connectors of the switch matrix. So I'm on pin 9 of the column and pin 1 of the row. You can see on the switch matrix here, column 9, row 1. So I'm across the TAC9 lamp. So in parallel to the switch matrix, I've got my my own circuit across lamp 81. So the test leads run down to this breadboard. This side of the circuit is from the circuit that I showed earlier. This side is new. So I've got the same 4N25 opto with power coming in from the column side through a diode and a limiting resistor going to the IR LED, and then grounding back at the row of the switch matrix. So this side's running 16 volt on the switch matrix, sorry, the lamp matrix. And then on this side I've got 5 volts from a wall supply that'll light an LED when I turn on the TAC light. So I've got the machine in test mode. You can't see the DMD, but it's in lamp test mode. So if I light up the right TAC lamp, you can see as the TAC lamp blinks, the LED blinks too. It's pretty stressful the first time I turned this on. I was hoping I wasn't going to blow up my pinball machine. But this is great. It shows me that the theory works, and I can get a signal off the lamp matrix. And even when I switch to another lamp, you see the LED is not lighting, at least not that I can see, and not lighting at all. So I don't know if the IR LED in the opto, if that has enough reverse voltage resistance that I could get away without having this diode. I think it probably doesn't. 16 volts is probably a lot for that little IR LED. So if I took out that diode, I might see that LED light when other LEDs are on. And I might even screw up my lamp matrix so that on the pinball machine you'd see other lamps light when this one lamp is on. Anyway, I'm pretty happy. This kind of paves the way for the rest of the circuit. I moved the opto circuit that used to be on this breadboard over to this one to consolidate everything together. So when I integrate with the machine, I can just move this breadboard over with the power supply and the tach. I've started looking at how to lay out a board, a PCB, and get it fabricated. That's taken a while. There's a lot of pieces on that board that need to be put together, and spec'd out, and ordered, and laid out. So to tide myself over, I've been working on the code. So you can see I've made some changes to the board. This opto circuit isn't connected. I need 12 of those to read the tach signal from the playfield. And I don't have 12. And I don't have room for 12. So to get the code set up, I had to simulate those inputs. So all of these wires looping over the top go from the I/O of the basic stamp to this bank of dip switches, and those are simulating some of the tach lamps on the playfield. I'll show you how it works. I'll fire it up, and the tach will go through its test mode like it did before, and then it settles at the lowest level. So from right to left are increasing levels of the tach on the playfield. So if I flip this switch, you'll see the tach raises, and as I flip more switches, the tach keeps raising. Now I only have 8 different switches here, and I need 12. So I've had to stop short. But you can see when and this last switch, in fact, is the mode switch, which I'll talk about later. But you can see when I flip this last tach switch, this light lights up. I'm intending for that to be the shift light. So I think I'll order a little automotive tach light. I actually used to have one on my Honda Prelude. But I sold it, so I'll have to order another one just like it. So that's going to be the red line switch, or the red line lamp, and that'll cause the shift light to come on and off. As you can see, as I back down off the tach, the needle drops back down. And in fact, if I raise it up to the highest level and I undo all the ones below it, the needle doesn't change. But once I drop that highest one, it goes all the way back down to 0. So aside from only having 7 different levels, this is how I think the tach's going to respond to the lamps on the playfield. I was hoping the needle would respond a bit faster, but there's a lot more code to get this done than there was in previous versions of the program. So I'm gonna have to look at optimizing to see if I can get the needle to respond faster, especially at those lower levels. It's really slow. Maybe I can step multiple times. Right now it's only stepping the potentiometer once every program loop, so maybe I can step multiple times at the low levels. Anyway, I think it's pretty cool. So I've moved the breadboard over to the machine so I could hook it up to the lamp matrix. I've got the opto hooked up to the same lamp that I was hooked up to before. And I've got the board and the tach powered up. I've got the dip switches set to bring the tach needle up to about 3 where it was before. But it's not there right now because the mode light that I'm using to determine whether I should pay attention to the tach input on the machine is turned off. So I'm expecting in the final product that I'm going to use this first lamp down here, the first white lamp of the tach, to determine whether the tach is actually showing an RPM signal, because sometimes during play and during attract mode, the lights on the tach just spin. But whenever the tach is actually displaying the RPM, that first light is always solid, and then the rest of the lights vary depending on the RPM. So I know if it's not consistently on, that I shouldn't listen to the tach signal. So because it's not on, you can see the tach is at rest. So the lamp that I have wired up on the lamp matrix isn't this first one, it's actually this lamp up here. I've got the machine in test mode. You can see when I turn on that lamp, the micro senses it, and it applies the tach signal that I have set. And when I turn it off, it goes back down again. So what I'm thinking is when we're in attract mode, or we're in a mode where we're not showing RPM, I'll just have the tach sit at rest. And I was thinking maybe I could even turn the illumination of the tach off so it draws your attention away from the tach. So I've got a window that I use to determine whether the lamp is on or off, because the micro sees the lamp flashing. Even if the lamp is solidly on, like right now it's flashing, but during gameplay, if it's solidly on, the micro still sees it flash, because in reality that lamp, because it's a matrixed signal, is flashing all the time, even when it's solid. So I've got a window that if the lamp has been on for a certain within a certain number of program execution loops, then the micro considers it to be on. So that's why when I turn the lamp off, the needle stays up there for a second. That's because I have a pretty long window set. And I had to have a long window set because the lamp is flashing. Normally it would be solid. And I could have a shorter window because I'd see more of the lamp being on. Right now I see a lot of it being off, and I rarely see it on. So I had to make the window long. So I think the tach will be more responsive in the final product when I get the final code, and I can tweak that window to make it smaller. This is a pretty big step though. I'm integrated with the machine and actually making the tach move based on the lights. Pretty cool. So let's take a look with the logic probe. We can see on the 5-volt side of the opto. So there's the opto IC. This side is the 16 volts from the lamp matrix. This side is the 5-volt side that goes to the micro. I've got the tack lamp flashing right now, so we'll be able to see the signal change on the opto. So that oscillating is coincidental with the lamp flashing on the playfield. So you can see it's normally high and it pulses low. Let's turn the lamp off. And you can see it always stays high. So when the lamp is on, the transistor in the opto grounds this signal. So when the lamp is on, the micro sees a logical 0, and when the lamp is off, the micro sees a logical 1. So I've got the game in attract mode. You can see how the tack lights flash. The one I'm keying off of right now is this one. So it flashes maybe once a second or so. If we take a look at the output from the micro, every 250 cycles, program loop cycles, I have it outputting how many times it saw the lamp on, and then the threshold for what I consider to be really on, and then that's just the number of cycles. And here is what that causes the lamp to be interpreted as. So you can see that we're seeing the lamp turn on. Not very often, because it's just flashing. It's not enough to break the threshold and cause the lamp to be interpreted as on. So we'll go back and cause the lamp to be on more solidly. I'll fire up a game and get the tack to turn on. There. So you can see the lamp is solid, and we'll go see how many times we see it turn on. So it's definitely more. We're seeing between 18 and 20 cycles out of 250 cycles where it's turned on, and it's enough to trip that threshold and cause us to interpret the lamp as being on. Like, one of the problems is, like, I can't insert this kind of instrumentation and look at these values without affecting the results, because this slows down the program to output this serial data. And I think it may be the case that the micro could get on the same kind of frequency that the lamp matrix is on, and I might see a couple really low values in a row that would cause the lamp not to be registered as on. So I'll have to mess with the thresholds and get the code in a more final state to see what the timing is like. It's not going to be a perfect science, I'm afraid. I've been formalizing my schematic to prepare for PCB, a printed circuit board manufacturer. I've been laying out the features that I want on the board and the different components that I need, trying to get a bill of materials together. It started to get kind of cumbersome to keep updating this old pencil sketch, so I digitized it. I used Visio. I use Visio at work a lot, and I didn't know that there were shape libraries for the typical components, like resistors and capacitors and such. But there are, at least in Visual Studio 2013, there are shape libraries for that. So it was fun to work in a tool that I was comfortable with, and it allowed me to make a lot more revisions a lot quicker than I would have been able to in pencil and paper. Let's take a look at the circuit, because I've made some changes. So around the outside are the connectors around the left and the right. At the top here is the 12-volt input. Now that's the only input to the only power input to the board is that 12 volts, and then a ground as well. So the major components are the plus minus 5 volt power supply here, the digital potentiometer here, the voltage controlled oscillator here, the basic stamp, the opto couplers. There'll actually be 12 of those. And then some stuff that I just added. The TAC power and TAC signal, and also a power for shift light. So let's take a closer look. So around the optos, we've got the lamp matrix columns coming in. So there will actually be 8 pins of interest on this connector. The lamp matrix rows coming in, also 8 pins. And since we're running a circuit in parallel with the lamp matrix, I've got to feed those back out again. So we've got columns and rows going back out. So as I said, everything in this box there will be 12 of. So we're looking at 12 different lamps. So we'll have 12 optos. Moving up, we've got the basic stamp. I added a couple external connectors for the stamp. There's a reset switch, which I think I'll use in the machine as just a way of calibrating the tack, or at least watching the tack needle go up to peg out and then go back down again. So it's a way of just making sure the tack works without having to start a game. And also this debug header. This is a DB9 RS-232 serial port. I was hoping to not have to include this on the production board, but I think I'll probably have to tweak the code on the basic stamp after I get it installed in a game, and it would be impossible to get any debug output from the stamp when it's installed in the game unless I had this header. Like, I can take the stamp out and put it in a developer board to load new software, but getting debug output, I've got to have this header. So I'll install at least on my own machine, I'll install a DB9 connector. If I ever give or sell this mod to anybody else, it'll probably just have a header. I probably won't include the DB9 connector. So These pins are just for that debug output. This is actually 12 different pins, the I/O pins that go to the opto. This pin goes to the shift light. These 3 I/O pins go to the digital pot, which is up here. So here's our digipot, which connects to the VCO here via this trace. None of this circuitry with the digipot and the VCO has changed recently. I've been looking at maybe using different values for the timing capacitor and the timing resistor over here. But for now, I'm sticking with the originals. It seems to work pretty well most of the time. When you graph it out, it's a little bit off. That's why sometimes the tachometer pegs at 8, and sometimes it pegs at like 8 1/4. I think if I went with some different values, I could probably get it closer to 8 and get it more consistent. But for now, I'll stick with these 2 values. So I added the ±5 volt power supply up here. All the power for the basic stamp and the different ICs come from this board and run on that regulated 5 volts or negative 5 volts. That board is in turn powered by a 12 volt input, which actually I've got drawn up is coming in from over here. So there'll be an external connector for 12 volts and ground. I put in some test points so I can measure the incoming 12 volts. I'm not sure if I'm going to run it from the machine, because the pinball machine offers I think it offers a 12 volt bus that I could leverage. I'm kind of hesitant to run it off that because I don't want to stress that power supply too much, and I'm not even sure yet how much power this circuit's going to draw. I know this supply is rated up to an amp, so I hope I'm not getting above that. But once I get it all wired up, I'll have to see exactly where I want to take this input from. Anyway, there's test points, so I can make sure, regardless of where I get the power, I can make sure the power is good and steady, and an indicator to indicate whether the 12 volts is on or not. I don't have an indicator for plus and minus 5 because that's actually on this board. There's 2 separate LEDs on that board. So over here are the outputs for the tach and for the shift light. The tach signal is driven by the VCO that comes in over here. The tach illumination, the tach power goes straight to 12 volts, which is this bus here. And then the tach ground comes from the ground bus, which is here. The shift light I added recently. I've got one more I/O pin left on the basic stamp, so I thought this would be a pretty good use. So when we hit red line, the shift light will come on. So that's controlled by Q2, and Q2 is connected to that one last I/O pin on the basic stamp. And that's about it. It was fun laying this out because I love Visio so much, and it's a lot easier to make changes to this than it was the pencil drawing. One of the more recent changes to the circuit that I've made is in the opto. I'm using 4N25 optos, and that particular opto offers not only an input anode and cathode and output collector and emitter, that's typical, but also a connection to the base of that output transistor. The example is for the 4N25. Even in the data sheet that I was using from Vishay, leave this base floating. And there's not really any information about what you're supposed to do with it. So on the original circuits that I made, the base was just floating, and it worked just fine. But as I was looking around the internet for more examples of the 4N25 to see exactly what to do with this pin, some people talked about connecting a capacitor to it or connecting a resistor to it. So I went to look at some other data sheets, and there was some more information on some other manufacturers' data sheets, specifically the Titron here. So if we look at the Vishay, we'll go look at their example circuit here. There's nothing coming off the base, and there's not really any information in their graphs about anything to do with the base connection either. But this Titron one, they show a resistor, the base emitter resistor. And I think the theory for that is this base has some capacitance to it. So when it reacts to the LED when it's on, that capacitance sticks in the base, and it delays shutting off this circuit. So even after the LED goes out, the base stays charged for a little bit. So it increases the amount of time here, the T off time, while that capacitance bleeds out. So a connection to ground through a resistor helps bleed that off a little bit faster. And also an open pin coming off the IC kind of serves as an antenna. If you got too much noise on your board, you might pick some of that up and get some kind of spurious closures of this transistor. So there's some useful graphs here on this data sheet talking about the resistance, the base emitter resistance, and how it affects your turn on time and your turn off time. So it's interesting and frustrating how the data sheets differ between different manufacturers. So on my schematic, I've settled on a 100K value, and when you see people using resistors on the base connection on the 4N25, that's a typical value for people to use. So 100K is this is already measured in K. So 100K is here. So this turn on time is normalized against open resistance, so leaving that connector disconnected. So with 100K, my turn on time is actually a little bit more than it was being open, and my turn off time is significantly less than leaving it open. In practice, I actually ran some tests, and in practice it didn't make a whole lot of difference. So my original circuit, that connector was open, so I ran with I had the light on the pinball machine was steady on, and I ran for about a minute. I ran my circuit and had the micro output how many times out of 250 times, 250 samples, how many samples did it find that the lamp was on. And it's pretty consistent. When I left it open, it was typically about 28 on average out of 250. I tried 51K, at the bottom of the scale, and it was still about 28, and 100K was still about 28. These values are the standard deviations. So it really didn't seem to make a difference in my circuit. I think it's not switching fast enough that I need a really accurate, a really small turn on and turn off time. But I feel better tying that connection to ground. It just didn't seem right to leave it floating. I had originally intended for the second part of this video series, to include both integration and fabrication. But I've only gotten through the integration part of this video, and it's already about an hour long, so it's time to cut this one off. I'll save fabrication for the next video. But I do want to talk about where I'm going next. So now that I've got my schematic in digital form so it's easy for me to work with, I need to get it into a format that's easy for fabricators to work with. There are several different file formats that PCB fabricators take, and there are lots of different software packages to make those file formats. Wikipedia has a comparison of these software applications. They're called electronic design automation software, or EDA. So you can see this comparison shows lots of different programs, and a lot of them are free. One of the problems with these programs is manufacturers will give you a free application, but that application ties you to that manufacturer. So the first couple that I looked at had that issue. I wanted to make sure that if I spend the time to make these files, that I'm able to go to many different manufacturers to use them. So I've read a couple of reviews online, and I like the sound of this one, Design Spark. It's made by a board manufacturer, but the cool thing about it is it doesn't tie you to that manufacturer. So RS Components gives you the application, but it spits out a standard file format that you can use in lots of different places. So there are some reviews online of this program. This guy had very favorable things to say, and it seems to be well documented. Eugene Tam has put out several tutorial videos that cover lots of different topics. So I'm starting to watch those to get some background on the application before I dive into it. So I'm excited to get this board laid out and get some hardware in my hands.
We're on his tail. Over. Roger, 504. Stay on him. Choppers, proceed to 504's location. Roger, dispatch. I can't keep up with him. Choppers, can you see the suspect? Roger, dispatch. I can see him.